So now come to our last event for today, the most exciting event, I would say. We'll have the brain, like the top engineers of ARM ecosystem. We'll have a panel discussion. So first I will introduce our host of the panel, our new HPC-SIG Senior Director, Elsie. So please. Elsie, before joining Linaro, she's Senior Director of Qualcomm's server division. Everyone actually questioned about Qualcomm server division now. What I can assure you at this moment is the brain has come to Linaro. So CCS. Okay, Dr. Masoka is the pioneer of HPC in Japan, and is also leading the convergence of AI deep learning on supercomputer. So we are very happy to have invited Dr. Masoka on the stage. And our second guest, Pak Liu. Pak has delivered a speech this morning, and he's a principal architecture of ARM Research Center.
Needs based on data accumulated from either observation or from the simulations. So that's HPC being augmented or replaced in some cases by AI. It's not always that this incurs heavy workload. Sometimes they do, sometimes they don't. Okay. So sometimes you may still have simulation. Sometimes you may the simulation, the resolution may be so big that the AI part, the machine learning part, may actually become quite comparable or even bigger than the simulation. Still, you get great savings in time to solution. The other is accelerating HPC machine learning via HPC. So get more data sets, more get more faces in the cloud to recognize. So you have to use more HPC to methods to, for example, reduce the training time to some realistic measures instead of taking years, taking minutes. So certainly this whole scenario had been born by on the former the sort of the limitations of the growth of the compute power. So AI helping the situation. The latter have been the HPC enabling AI, because we now have, compared to the 1980s where people had the Hinton and those people had kind of came up with the concepts of back propagation, but the algorithms were just too expensive to be realistic. So in the 80s we had symbolic AI, which was not very useful. Like if you remember Prolog and those kind of things, they're not very useful. But now the computational power increased by 7 orders of magnitude. So now what would have taken a millennia can be done in a realistic time. So certainly we're on the birth of all this combination of the two activities, and I think this will progress even further as we move along. We get more compute power. It's sort of a bilateral interaction of we get more compute power to help AI helping to get more HPC.
It seems very symbiotic.
Yeah.
I think the key is computation power, because we are facing the end of the Moore's law. So traditional processor and DCP become another.
Little closer.
Hello?
People facing such kind of heterogeneous system, people try to use some solution for the operating system. But nowadays, on AirPod, people cannot just use operating system. People try to use IP. There are some issues that will.
No, it's okay. So in my opinion, I think well, AI is definitely like transforming HPC. It has it now gives a lot of hardware requirements into providing like the what the system should be for running some of the HPC workload in order to get the best economy out from the system, right? So I think economy has a lot to do with like when from a really realistic point of view, customers, want to get a system, they actually want to make even though you give them a general purpose system, they will actually try to make use out of as much as they can to get the best out of the system. Um, so something that we have been using in the past for HPC, and like anything on top of besides compilers and everything that we have done in the last last so many years, is that compilers, math libraries, you know, DGM, machine multiplication. Those are very important for driving like AI, machine learning, like training. So that actually been used quite a lot, with the introduction of AI. So I think, in my opinion, a lot of things that have been done before in the past, now we're just going to add more on top of it, just for supporting AI and training. And I think, from a user point of view, because Huawei actually supports our user very much, and we want to actually get advanced performance, and also the price performance for the server. Is that we will try to make use of the cases that to get the best value. But at the same time, we actually also try to, in my opinion, that make use of some acceleration hardware, together with together ASIC or FPGA or whatever that is, it, for the upcoming solutions that we're going to do. Ascent 910, in my opinion, is going to be also part of this solution. But yeah, let's leave it like that for now. Yeah.
No, very good. So I hear then that HPC is enabling a transformation into a more heterogeneous environment for the server clusters. Would you say that? Including.
Yeah, definitely. I mean, this is why that we want to come up with a competitive solution for ARM, or for in general, or basically try to deliver the first best performance, and also fill in the gap that, or if that's that's the hardware that's needed to support that kind of solution. So exactly what you said, the heterogeneous solution.
Right. What AI services do you see evolving with the convergence of the cloud, HPC, and artificial intelligence clusters?
So, from the perspective of okay, first let's take training. Okay, so training is very resource and compute cycle consuming, and oops, maybe two microphone like yeah, this works. It's very resource consuming, yeah, and it's not just the that's because training is very difficult, because you have to sweep over the different types of network configurations and hyperparameter search, as well as and there are various tricks and trades you have to learn to do in order to come up with a properly trained network that will be useful. Of course, you can use various techniques, but these techniques are not very trivial. So I think that the services to enable easing of the various handling of training, be it the handling of data sets, cleansing of data sets, to guiding a hyperparameter search, to coming up with the optimal resource allocations, and so forth, that will enable easy usage of training over these very large machines, which are fundamentally hard to use in the first place. We all learned that from HPC. Will be one of the core services on the training side. On the inference side, once you have these trained networks, you have to be able to deploy them. You have to be able to, and these deployment may be across different sets of resources. It may be on the edge, it may be on the cloud, it may be on some intermediary nodes from this edge to cloud computing infrastructure. So you need to maintain them, because you retrain your network, then you need to redisseminate your network. You need to keep on collecting the No, you may need to occasional back propagation to make sure that your what you train network and your once your accuracy starts going down, you need to detect these. So the edge side, if it's especially if it's large scale, all these services to uh, maintain this whole holistic network of artificial intelligence enabled devices will become one of the more prevalent services. The training inference itself is fairly lightweight, but to keep them running and keep them useful and keep them updated, maintain them is what's difficult, as is with any sort of distributed system. So that's going to so that'll be one of the core services.
Okay. Okay. Let me talk about the inference part. Yes. Because in industry, we see many different kind of products. Like for example, we see Marvell and WD, they try to add some accelerators in the SSD controller. And in Taiwan, there are some groups try to develop a kind of technology we call computing memory, make some accelerator in the DRAM controller. And of course, there are a lot of teams try to do the flash control, add AI accelerator in the flash controller. So in the future, you can see in one server, there are many, almost all the storage or all the memory they can compute. So I guess that will change a lot. Uh, that will change a lot HPC applications because we can try to do computation in the SSD controller. That means now you can say, "Hey Google, please help me to pick up the most ugly picture of David." Yes, and send the picture to him. You just need to say this command. Then the SSD controller will try to search all the pictures, identify who is David and monkey, and send the most ugly picture to David. Yes, that will be happened in SD controller. And what happened in the DRAM controller? DRAM controller also have ability to compute. So nowadays you can say, okay, please just help me to encrypt a chunk of memory and then make sure those data are safe. And of course, now you can think process itself just a big cache with computation power. Yeah, I think uh, this changes HPC, and now in the AI inference all happens. So yeah, that's what I want to share. Yeah.
I think I think to follow up what you said, I think it's also important where the data sits. If you on the inference side where you have the IoT devices or the hybrid accelerator, but you have on the very fast memory. You don't want to have too much data movement back to your data center because it will actually be very costly. So I think what you have said is also just to follow up what you have said. I think that's also will have the have some consideration when designing that kind of AI system or for data locality and also avoiding the movement of the I guess data. So like for instance, like you do recording of like photos or video, not necessarily they all need to be processed back to the data center. They can also be be inferenced back on the remote side. So this is something that to consider. Yeah.
Very good. So what I'm hearing you say is that there's more locality to this data now. So that sounds like that's one of the use cases that we're going to be seeing for HPC moving closer to the edge. What are some of the other edge use cases that we'll see for HPC at the edge? Yes.
Well, fundamentally, HPC at the edge is difficult because of power. Because there's always power limitation. And as we move towards this realm of limitations on the growth of compute due to the ending of Moore's law, the amount of compute that can be done on the edge devices will become more saturated compared to those data centers more quickly. I mean, that's that's a trajectory. So, and of course, you come up. However, the advantage of the edge is you can be more customized. That is, you can use, for example, you can try to use, there's some recent work try to do some convolution using analog circuits, which may not be very useful for things like training in the cloud because the precision is too low. But for inferencing, where fundamentally where precision can be a little bit more lax, and can be very tailored to certain types of resolution, such that these analog devices can be tuned to work work on very limited, very sort of limited sets of like image sensor arrays, then that can be accommodated. So so I think that HPC on the edge is more, certainly we will have these types of various types of inferencing, for example, to reduce the amount of data sent by, for example, detecting anomaly first out of the streaming sets of data. Then you kind of pick and choose which ones you send back to the data center for more closer analysis and so forth. So certainly the instances will be there. But don't expect all the compute to move to the edge, because that's fundamentally difficult because of the limitations of power. Again, this will saturate more quickly than what can be fed from the power grid from the power grid. So it's always a balance between the cost of moving data, which for wireless is becoming cheaper as we move to 5G and 6G, as opposed to compute, which will saturate because we have limitation lithography.
I agree with because the bottleneck for the edge computing is the power. So I think some area like a vehicle, some kind of craft they will not limited by power. For example, one of our customer they try to make 5 chips, and all these 5 chips try to care about the power consumption issue, but they still need some communication from the car, from the ADAS to the cloud. Yeah, and in this case, we try to leverage some technology. Most of them are try to do partition, scheduling, and allocation. Try to help all the system can work together without any trouble. Yeah, and so yes, I think if we have to facing a power limitation, then it's very difficult to ask edge device to do any kind of AI. But there are still many edge devices. They don't have such kind of limitation. Then maybe, in my opinion, there may be one direction. Yeah.
Well, same thing as what we have talked about. I think data locality definitely is an issue, unless we find a really a better way of transferring data back to the data center or among the edge devices or edge systems. It would be very hard to do like I guess HPC among all these like edge devices. Cost, or I mean it's not cost, but power and data movement is actually driving the too much latency among all these devices that are actually doing that computing. If you actually can find something that actually does not have much latency or much dependent on the latency or throughput or on the network that's among all these like edge devices, maybe actually you can find some use case that can work. Very, yeah.
I'll take a minute to see, is there any questions right now from the audience? Or we can carry on. All right, we'll carry on. But I know you have some questions. Okay, how will hardware or software architectures need to evolve to enable deep learning scale out across large clusters? And let's start with Pak.
How does hardware software altogether?
Hardware or software architectures need to evolve in order to develop for scale out, for large architectures.
Large architecture. Well, I think it's.
Yeah. Do you see new hardware buses or interfaces or ICEs necessary?
I think we have not. I guess. Well, from some of the things I've read, at least, definitely a very high throughput or better algorithm in doing something like collective algorithm or reduce this is actually involving like communication definitely would be the glue, I guess, in orchestrating that kind of like infrastructure. So uh, and I think that kind of development actually been or research actually been taking place right now to find a better way of communication. I mean, of communicating among all these like systems for deep learning. So NVIDIA has the Nickel library, but I'm sure that there are many other like research actually been done in communication to for better scale out kind of like machine learning training work. Um, so I think communication definitely or system communication definitely is something that is important that needs to be investigated on. High bandwidth for um, you know system collective operation.
Because I'm compiler guy, so I just talk from the compiler point of view. Okay, I think the one of the most interesting things maybe like that in traditional operating system and a compiler, they are handle different kind of level of computation. Sometimes operating system they try to handle process or big task, and the compiler we just try to handle blocks or some instructions. And nowadays, there are almost no communication between compiler and operating system. Compiler just try to emit a file format, then operation system loading it and try to run all the image to follow the instructions. But for now, take AI for example. Now we need more communication between compiler and operating systems. Maybe in the future the world will become like that. The compiler will try to provide or try to give some suggestions to operating system and put all these commands in the file format. Then the operating system will try to interpret this information and uh, try to decide take or not take. Yeah. And for AI, because many computation like convolution, they are actually a big task. Sometimes they're bigger than most process. So now today, compiler they have to provide some ability about predict the computation the demand of computation of each task. So I guess in the recent future, we have to define a kind of format to help operating system communicate with the compiler. Maybe compiler will put some hints to the operating system and make the whole system more effective. Yeah.
So this is one of my core research, so I can give you a great answer. However, I will do that tomorrow in my keynote. Just to give you a source, there are several. There are there are three major obstacles in scaling, or accelerating deep learning, and there are many. We're trying to be number one in the world on this, and we'll very likely be. And at the end of January, we'll probably beat Google and all the folks. We have beaten Google once, but we'll probably beat Google and become number one in terms of image training. Hopefully. But we will. But the three major obstacles. One is basically, as was mentioned, especially in data parallelism, basically it's a reduction operation. When you average the activations in backpropagation in data parallel training, if you look at the equation, that's exactly what you do. That has nothing to do with any other systems issues. It's the nature of the algorithm. And so that's one obstacle from a system standpoint. So you've got to have very high bandwidth. And Nickel has a half-hearted job of doing this. We hate Nickel because it has lots of bugs. And they never fix it. NVIDIA, are you listening? Fix the Nickel bug. Secondly, there is a more fundamental mathematical problem of convergence because what you do what you call a batch training, and when you do data parallel training, especially particularly be increasing a batch size. And by increasing batch size, basically what happens is so you have all these gradients, and the gradients go all over the place. So when you have say you go to 1,000 nodes, at least you have 1,000 batch. So I have 1,000 gradients you average over. So so you have to average 1,000. That's the optimization step you take in the back propagation. You don't know that's going to be correct. So convergence suffers. So empirically, it's said it's been shown that even after a few hundred batch size, a few hundred, convergence really suffers. It gets real slow or it doesn't converge at all if you just use a simple stochastic gradient linear descent algorithm. Recently, a group of people, including us, have been working on more sophisticated algorithm using quadratic techniques like what's called a natural gradient descent. And I won't go over the mathematical details of it, but it's promising. The only problem is it's expensive as hell. But we have several people over time, including us, we found algorithm breakthroughs to make the algorithm almost as fast as SGD now. So our most recent paper shows we can achieve batch, if you know this area, batch size of over 100,000, still converge on ImageNet. So thus we can go up to thousands of nodes. The third is when you have very large data sets like very large images like medical scans or like 3D data or like very large, or if it's a graph convolution, very large graphs of very large variety in the vertices, then the network plus the data, especially when you have batches, doesn't fit in memory. So it's been known that for very large data sets, that even if it fits, the batch size only becomes one, then becomes hopefully very inefficient because you do want some reasonable batch sizes in order to make things go faster, because then you keep on then becomes an I/O problem. So how to handle very large data, very large memory by exploiting a memory hierarchy. That's another one, and how to do so using the nature of the convolutional neural networks and their algorithm. And we have have done work on that, and so that's again another challenge. There are even more challenges. So the architecture can help in various ways, for example, but most of the architectural help is in terms of increased bandwidth in the system. Because if you have very large memory, it helps you move the data around between the memory hierarchy. We have a very large bandwidth or between data nodes. For reduction, yes, this helps too. Second order methods, well, it's a little bit, it's a little bit of a toss-up, but you still have to do have to do some operations which are bandwidth limited, and also the convolution kernels. Sometimes you pick these bandwidth limited, bandwidth rich kernels because for certain reasons. So all in all, the architecture should not just increase flops, as a lot of these deep learning hardware tries to do, which is a total mistake, but rather you have to increase the bandwidth and generality. And the ARM processor, including A64FX, which we're building, will be perfect for that.
I think need a more hardware specific acceleration hardware for the ARM server, or we are going to move the SPU or something.
Are you asking about the training or the edge computing?
Yeah, training.
Oh yeah. For training, like I said, the algorithms are becoming increasingly sophisticated as we move to larger batch sizes. Like I said, we go from linear methods to quadratic methods, for example. Then it becomes harder and harder to have very simplified hardware to handle that. It's nowadays people don't do gem-based convolutions anymore because it's slow. Rather they use WinRAG methods or they use FFT. Those are faster methods, but they're more complicated because you need to do the spatial transformation. and so you need um, however, but to some extent, when you grad, for example, can be accelerated to a little bit by using DGM accelerator, just like tensor cores. But it remains to be seen where the exact balance is in terms of the achieved speed up versus hardware specialization. Some people believe hardware specialization still has some room. Um, I personally believe that there's not much room left for specialization rather than the standard specialization you do on ARM or GPU. Just add some, some tensor or matrix engine to the standard cores could be enough. Yeah.
From a business point of view, of course, we welcome there are a lot of accelerator in the industry, but I think there are some, how to say that, because some people believe that if we can add more SRAM or add more Mac, then we can make the deep learning inference or training faster, but it's not true. Yeah, because deep learning model, they have many different kind of type. Some are memory, some are computation density, or some are memory density. So I believe in maybe 1 year or 2 years later, people will fully understand if you want to do such kind of AI application, then how many accelerator, how many Mac, and then how big of a strength they will have to be used. Yeah, but I don't think the number of accelerator or type of accelerator will um, become more diverse, or we will or more solution in the industry. I think that will not be happen. Yeah, there will maybe several big or several popular accelerator dominate the industry.
Well, you know that from Huawei's perspective, we will have our own accelerator for machine learning, so for training. So so I think it will have the right requirements that we need to satisfy our use cases and for customers for first a good enough performance. Second is um, well price performance economy and also easy to use maybe. So this is pretty much what in my opinion is always like customer driven. So as for the requirements for the hardware. So we will have such a solution later on.
And post K, right, for the and for AF and 64X CPU, the HBM2 is supported, right? So and HBM2 is also very popular in GPU cards, right? So this is very important to improve the memory bandwidth. But is it maybe can it be a general solution for the generic servers, right? Previously we have the DDR memory, right? So we have the system memory for generic servers, right? We can have, for example, 64 or maybe even bigger memory. But I don't think the HBM memory is suitable for such kind of type at the moment because you integrated the HBM memory with the processor directory, right? So how we can improve this part in the future to have better memory bandwidth just with a CPU solution?
I think it's, in my opinion, it's a trade-off. You put a high bandwidth memory instead of traditional memory. Then you think about how big of a size of the silicon, I mean, of the chip was going to be, and also being able to support on the memory side. So it's a, and then it actually affects how much space or how much storage you can have on the memory. So if you want to design something more general purpose, uh, you are trading off the size that you think that maybe your customers is actually gonna need for running their HPC applications by using high bandwidth memory. So far this is something that I've observed. So maybe this will change in the future, but I just at least that is the way I take a look at it. I mean that is my take on it. So.
And I think there are two roles Papa might. The first, general means expensive. Yeah, and because we have very different type of AI application and their behavior in the process are very different. So from I don't think there will be some hardware solution to support processor has better bandwidth on the bus or has better bandwidth to communicate with memory. But there may be some compiler solution. Take for example, our compiler can reduce the memory consumption about 46% than the other solutions. That means if you originally you may need about 1 megabyte byte DRAM, but after our optimization, you may need only 50 megabyte DRAM. Yep. These are all compiler solutions. But from the hardware solution, we didn't see any good solution in the market. Yeah.
Yeah, so you got to question why do people use large memory? And my answer is because they're lazy. For the following reasons, not to blame them. So, okay, so in principle, you shouldn't need that much memory. Okay, because what happens? Well, you need some reasonable size memory to put the operating system in. And so you need memory to put your data space. But okay, so let's think of the following: if you have very efficient computing, be it bandwidth, a recent paper like Wahib and I have written demonstrate basically that most of the codes are most of the modern codes are HPC codes are bandwidth bound. Okay, let's say I have a bandwidth bound code. What is the runtime proportional to? Okay, is it the amount of memory? No. The runtime for bandwidth bound code is usually proportional to the memory capacity. Okay, and that's because basically bandwidth bound codes, they tend to scan the entire memory space. Take any sort of CFD code, they scan the entire memory space. So you're limited by your bandwidth of how much you can scan the memory, how many times you can scan the memory per second. That's your limit. Okay, so but how do you increase memory bandwidth? Do you increase memory? No. If you increase memory, if you have twice the memory capacity, your runtime will be doubled. Okay, so it's bad. So for bandwidth bound code, increasing memory, having a processor that accommodates large memory is bad. So what do? Well, you increase the memory controller, you increase the memory port by 2. Okay, then your time solution will be halved. How do you increase the memory controller? Well, you have more CPUs. Okay,
Yeah,
you
correct.
double number of CPUs.
Yeah, correct. In this case, you with current maybe generic maybe DDR design, right? It is not easy to achieve, right?
Yeah. So that's why we went to HBM2, right?
Yeah. Yeah,
right.
right.
Because now I can make the same argument for actual dense linear algebra based codes too. In fact, they're bad because they have more complexity. These dense codes have like quadratic or even cubic complexity. Then you don't want to increase memory at all because if you have very large data sets, the runtime will explode. Okay. So again, you want to keep your data sets to be as small as possible per processing unit per LU. Again, you want to increase the number of CPUs. Okay, the same thing. So, having very fast memory while having modest amount of memory is a very important design in HPC space. And this is not just my thoughts alone. This is shared by people like Algera, who designed Fuji and now the Intel Fellow. Right? Al has exactly the same principle. That's how the nice landing is designed. So you should not have machines that have excessive memory per capacity per any sort of processing unit. So why do people design machines with very large memory? Well, because to accommodate 2 use cases. One is very large data. The only time this doesn't work is when you have random access to memory. Right? Mm-hmm. When you have random access to memory, you want some almost like, well, it would be NUMA, but fairly low access, low latency access to random portions of memory, like hash algorithms or like using databases. And your database, like your Oracle database, might be big. So that's why people buy these large memory servers, because they try to have in-memory computing, but they have these hash accesses. So it's no longer bandwidth bound. It's order 1. Okay, so that's why large memory helps. So that's one scenario is database. So scenario 2 is when you have any sort of program language which are interpretive and do garbage collection. Then, because you move the objects around, usually these are copy-based object, or at least the random pointers go random. So basically, and the processing is slow, like Java or Python. So in that case, again, you want to have, but because your data sets all have lots of overhead, so you try to keep them all in memory. So that's why you want very large memory space because you have no control over memory. But why do people use those Python? Because they're lazy. Okay. So okay, why do people use databases? Well, maybe not because they're lazy, but at least they cram everything in the Oracle database and just write a wrapper, SQL query around to create an application. So most of the general purpose processors, that's where the money's made, right? And that's why they make a processor be latency sensitive by having very deep caches, and also, but have the less robust memory system. Although like Intel cores are very robust in terms of bandwidth, if you look at the memory system, they're designed for latency, which is very different on the A64FX because we ditched all those apps. We ditched. So other people make other ARM processors which are better, like Intel, better for those purposes. We ditched interpretive language. We ditched Oracle databases. But we focus on HPC. In that case, you want modest memory, fast memory, and lots of memory controllers and LUs per capacity. That's how A64FX works.
Okay, very good. Thank you.
Okay, so coming from both an x86 and ARM background, I'm very excited about standards and the role that it's the diversity of the ARM architecture. My next question to the panel is about standards. What standards do you see are missing inside of the HPC ecosystem in order for Linaro or the ARM ecosystem to enable to have a successful ecosystem for HPC? And who's first? So we started with.
Since I have to go in a few minutes,
okay.
I will. So this convergence of HPC and AI and service-based computing, there requires that HPC would adhere to the service-oriented requests coming from the network, and some of that, of course, can be done with some certain type of services. But if you want more direct tie-in of the HPC services to the broader, broader web programming community,
yes,
that's where it's really still very lacking. So even now, when we look at for example, when we look at batch schedulers, there is no standard on like REST API for controlling the batch workload schedule. So that's why the web community basically embedded its own, but it's kind of geared towards that kind of style of workload, more real-time response type of workloads. It's not aimed for things like batch queue, intricate batch queue control. So if there are standards, then all these web services type of applications can, no matter what kind of workload manager you use, can tie into those. But because it's so fragmented, each workload scheduler, be it like Innova or PBS, whatever, they have very different APIs, REST APIs. So we need basically to define the REST APIs for majority of services we provide from the HPC system to control the system. That's where it's at.
From my point of view, now from the AI part, now we are like a standard like ELF or Mark O in the Mac. It's just a kind of file format to describe how we load and how we interpret the whole system. Yep, and in traditional like GCC, we have ELF, and in Mac we have Mark O, we have PE in Windows. But for AI, we are facing heterogeneous system and they have many different kind of RTOS or runtime. But we still didn't have a uniform format to tell compiler or tell operating system how to dispatch different kind of session to different processor, how to put data to different segment of memory. Yeah, I think that may be one of the most urgent spec that we need in AI industry.
I think from a general point of view, I think ARM actually has a really good specification already, more predictable than I think for other architecture. If you actually look into like yeah, they were actually not processor counter, but it's also memory synchronization, memory operations, and for x86 actually is or other architecture is not it's predictable in some way. So I think in that point of view and more lower level actually, ARM actually has done a better job. Or user level that I work on mostly, for supporting customer. I think we're pretty much in the same boat on the together with x86 and ARM together. So it's not too much of a. I mean, we try to kind of like even out, to have a smoother transition for our customer. So I think what we have currently on the higher level, in the, I guess in user application space, we already actually doing pretty okay. But yeah.
Oh, good. That's very good to hear. Thank you. All right. As we begin to wrap up, do we have one last question from the audience? Going once? Going twice? You want dinner? Okay. Thank you very much, and thank you, panel.